All right, let's have a look at just at that homework I handed back. So what was on there was that dot product stuff. Now, on the first dot product problem, this one here, if you want to find the shear vector, what you got to do is take the total vector, the force vector, AC, and then subtract off the compression vector from it, okay? So that's how you would do that. So that's something I thought I'd mention based on what I was looking at when I was grading this stuff. So on this thing, when you get the vector for the compression, which is what you can find there, you do the dot product, and I think most people got through that pretty well. Once you've got that, if you want to find the other vector, so what you got here is you got FAC in vector form. What that is negative 5404, because it's going in the negative x direction. We got 7205 for the y, and then we got 3602 for the z. All right, and then what you want to do then is find the compressive force with the dot product, and I think most people got through that okay. And what we found there was 2338. So then if you want to find the compressive vector, what you do is you take the 2338, which is the magnitude, and then you multiply it through the unit vector that goes in the direction of the compression, which is right there. It's UAB. All right, and if you do that, you'll come up with the compression vector, minus 759, 1138, and negative 1897, okay? So that gets you the compressive vector. So to find the shear, what you do is you realize that the compression and shear are two components of the total. So what you can then do is take the compression vector and subtract it off of the total force vector, okay? Like so, and then what you get to is the shear vector, okay? So that's what's going on with that. And the shear vector then comes out to be negative 4645, 6067, 5499. That's what I got. Yeah, okay. Okay. So what I'm doing there, I'm using the fact that the compression and the shear are two components of the total. That's what we're doing there. They're at right angles, so you can add them up and get the total. So you can just rearrange that algebraically and come up with the shear. Okay, so that's how that goes if you need that shear vector. All right. So that's one thing that I wanted to mention. So we're good with that? Okay. All right. And then the other thing is that angle of the cable. It's 45 degrees. See what's going on with that cable angle? That's on 173, I think it is. All right. So on 173 here, this one. Okay, what's going on there is this is free to swing any which way it wants, and you've got equal forces. So they're both pulling with that 294 newtons, I think it is. And they're equal, and the one's in the X and one's in the Y. So that's going to end up just pulling to 45 degrees. It's just an equilibrium thing. Okay, so that's what's going on with that. And there's a lot of ways to express that and to kind of come up with what it is, but that's the basics of it. Okay. So are we okay with that? All right. All right. Just pause here for a second, I guess. All right, so what we got here on this test potentially is we've got the 2D vectors and the resultants, like what we did at the beginning of the class. Okay, so you should be able to do that. We got the 3D vectors. A unit vector is a total force vector divided by its own magnitude, and that equals the direction cosines for the force. Now, I'll mention for those of you online, I just handed this out in class, this review for the midterm on Monday. It's available online. It's a download. You can get to it there. It's under the exam or test review downloads or exam downloads, or whatever the heck I call them. It's down near the bottom there. Okay. If you want a force vector, then you can take the force magnitude and multiply it through the unit vector right there. Okay. Now notice we do things a little bit different than the mathematicians do. We don't put those absolute value signs around magnitudes. If it's bolded and it's typed, it's a vector. If it's not bolded, it's not. Often we might put vector arrows on top also. All right, so if you've got the angles with the three axes, you can take the cosine of them, multiply them by ij and k, and multiply the magnitude through, and you will get the vector. Okay. We did some double projections also. We had one problem. If I had to guess, I'd guess it was problem 143, but I couldn't swear to it. I think that's what it was, with those double projections. Then we did position vectors. Okay. Remember, RAB is RB minus RA. Remember to switch the order. Then we did dot products to find projections. Okay, so we got vocabulary here. A vector versus a scalar. A vector has direction, a scalar does not. The resultant is the sum of a certain number of vectors. The magnitude is different than a vector. If I ask for the magnitude of a force, I just want how big the force is. If I want a force vector, I want the ijk components. Then we have projection, projection along, tension, and compression. Those are all similar things. They're all projections along a line. In 3D, you use the dot product to find those, okay? Then we got projection perpendicular to and shear, okay? Which is the component normal to the axis you're looking at. So I'm not going to say find the projection of AB onto line BC. I'm going to say find the compression in BC caused by BA, okay? So just be aware how I use the vocabulary, and you should be familiar with those words.
So the compression is equal projection?
I'm sorry?
The compression.
Compression is a projection, right?
Okay.
It could be compression, it could be tension. They're both what are called axial forces, which are found by doing projections. Okay, component parallel to and component perpendicular to are more of the same. So component perpendicular to is the same as the shear, which is the same as the projection perpendicular to. They all mean the same thing, okay? Okay, Cartesian vector just means an XYZ vector. Angle with the blank axis. So I wouldn't say find alpha. I would say find the angle with the x-axis. You have to know that that angle is alpha, okay? Equilibrium means sum of forces are zero, moment about a point, and then moment about an axis. So those are all terms you should be familiar with. Okay. Okay, we did 2D particle equilibrium using right angle trigonometry. 3D particle equilibrium using more of a vector and kind of matrix approach. Put the vectors in columns, solve out the rows. Then we did 2D moments, m equals fd with d perpendicular to f, and then you use x and y components. And then we did 3D moments, r crossed with f. You've got the cross product formula on the bottom of the formula sheet. Okay, you'll get a new formula sheet for the test, okay? So you don't bring your own, I'll give you a new one, okay? So you want to look that thing over and know where the formulas are and what they look like. Okay, so you get r crossed with f. Remember to do it in that order, cross r with f. Remember, there's a cross product formula right on the bottom. Okay. Remember that r goes from the point to the force. Okay. And remember to do things in the correct way. Okay, I will look at your method, not just your answer, but your method. Okay, so show me the work. Okay, and then if we want a moment about an axis, we do a dot product. We dot the moment vector with the unit vector for the axis. Okay. Okay, now a couple things to remember on this. One is bring a non-programmable calculator. Practice using the calculator before you come here. Okay, that's important, and I keep saying that, but I want you to remember it because I've had people who did not do that, and that didn't always go well for them. Okay, so just be sure you know how to use your calculator before you come. What else? Okay, now this is a test. It's your job not only to get an answer, but to show me how you got it. Now, you don't need to impress me in overkill because you don't really have time to do that, but I need to be able to follow your steps because I give partial credit. I'm much more concerned with the method than I am with the answer at the end, but it's your job to show me what you did, okay? I've had people who question how I graded after a test, and they start explaining to me what they did, and I kind of put my hands up. I go, no, it isn't a verbal explanation. You're supposed to write it out so I can follow it. That's your job, okay? Okay, you with me there? And see, that's a skill for engineering. You got to be able to do that when you're doing calcs. Just show people what you're up to. Now, don't overkill it. I mean, you know, but make it clear, okay? Yes?
Would you say the format we've been using to answer our questions on the homework would be an acceptable level of
Yeah, it is, with the one exception, don't make your own sketch. I mean, just use the sketches there, modify them and go, and just lay it out so I can follow it, that's all. I mean, you know, I understand it's a test and you're in a rush. I'm not being unreasonable about this, but I'm just saying, if I'm gonna give you partial credit, I gotta be able to follow it.
Okay.
Yeah, that's the thing, okay, really. Okay. All right, so we got that, you know, that's pretty much it. Now the way I'll format this, if you look at those problems there, I gave you some sample problems for those of you online. They're there as well. So what I'm doing there, problems 1 through 4, I'm having you find some vectors, okay? So just find a bunch of vectors for me. 3 force vectors, and then position vectors and unit vectors. And then on the back, you'll see the same physical setup as you see on the front, the same dimensions and everything. And I'm saying use those vectors off the front to solve the stuff on the back. I'm doing that to save time, okay? So don't find the vectors all over again when you do it on the back. Use the ones you already found. Another technique I've used is I've put a bunch of vectors on the back page. You can pull it off and you can use them when you do this stuff, you know. So that's another way I might do it, okay? But just be looking for that. Don't be wasting your time. Okay, then we got a few others. Find the resultant of F1 and FAB, and then find the equilibrium there in those cables. And then problems 5 and 6 are what? You gotta find the compression in AC caused by FAB. So how you gonna do that? What's the operation to get that done? Dot product, man, okay? So you're gonna do a dot, okay? And then the next one, find the moment of FAB about point C. How you gonna do that? Yeah, okay. Cross, yeah, do a cross, okay? So that should be in your head when you're here. You know, you don't want to be scratching your head figuring out, you want to, do it when you get here on the test, okay? You want to know those things. Okay, now I've got like a kind of a flow chart. Somebody wanted one once, so on page 325 in your packet, I've got this 3D flow chart. I don't know if it's worth much or not, but it's in there. That has kind of the processes for doing some of these things. 325 kind of sticks in my mind. Yeah, there it is, okay. I don't know if that's of any use to you. I don't know if it is or not, but that just has some of the how to solve stuff out kind of on it, okay? All right, now I'll get you some of the partial answers on this review. If you got any questions, we could cover them probably on Friday, so I'll give you a little time to be looking it over, okay? And then Friday we go over this if you like. All right. So got any questions for starters now? bring a photo ID with you this time too, if you would, especially the online students. Yeah.
Do you know how many questions it's going to be?
I don't. I haven't written it up yet. I would normally my questions are what you're seeing are pretty typical of what I do. The wording's pretty standard, you know. Yeah, I've had on this one. Let me just think. Maybe 7 questions.
Okay.
Now some of them kind of short, like those ones at the beginning. Then maybe a little bit more in depth later on.
Yeah.
So something like that. It's not like 30 questions. It's nothing like those little short answer kind of things like some instructors do. I don't do it that way. Mine are longer.
Okay.
They're like homework problems, really, is what they're like. Okay, that's what I'd be looking homework problems over to get ready for this thing. Okay, and this thing ends at moments. Okay, the stuff we've been doing here the last couple days will not be on this test. It ends at moments, is where it ends with the stuff that you're turning in today. Okay, all right. So we got any questions there on that? You doing all right? Okay. All right, now let's have a look at, this is what I wanted to copy off. There's a little bit of a problem here that, why don't we have a look at it? Why don't you find a couple people you could work with on this, and let's see what we might do with this one. And this again is in the downloads for those of you online. It's called 3D Review Problem 2014. It's in the Moodle page downloads. It's under the homework downloads. You know, the test review is under the test review downloads or whatever I called it, but this is under the homework downloads. So why don't we start in on this, and why don't you find a couple people you could work with, okay? It's nice if they're in your major, but they may not be. I mean, whatever. Just find some people you can interact with and help each other through this. So what we got here. All right, and just introduce yourselves. Get the names down. All right, so what we know here is we've got 5,200 newtons in that cable. We've got the coordinates on everything. So that's another thing for this test to get ready for is reading those dimensions. And let's see if this shaft is going to break. Okay? So let's see if this shaft, and the fancy engineering word for breaking is called failing. Okay? So is this shaft going to fail? So if we apply that 5,200 newtons, and we know what the shaft can handle. The shaft can handle 12,000 newtons in compression, 3,000 in tension, and 6,000 in shear. And at A, we can handle a moment at 22,000 newton meters. Is this shaft gonna handle that 5,200 newtons? Okay, so let's show your work. Okay. So why don't we start on this? So what's step the first here on this? Do you think? Yeah, I think get those coordinates figured out, okay? So let's get the coordinates figured out. So those of you online, I'll pause the recording here periodically, okay? Because you don't need to be just listening to all the silence in here while people work through things. Now, if you like, you can post questions about this on the forum that I have set up. I think I got one in there in Moodle, so you know, if things come up, other students, or maybe I could jump in there if you got questions about it, but I'll pause it for now, okay? So find the coordinates of those points. All right, so what do we got here? Do we got minus 2.4, 3, 3.6? And then do we got 0.9, 1.6, and minus 2. And then we got, now notice A is probably the one that's the most interesting. That doesn't have any x, does it? There's no dimension in the x direction, so x is 0. 5.8, negative 0.4. Did I get those right? Any questions on those? Because, you know, now a couple of things on this. I mean, you know, we don't want to get a bum number here, because if we do, boy, everything blows up on you, right? Okay, now this is a very good reason why you got to show work on tests. You know, if you make a little mistake on one of these, I take a point off if I can follow it through. But if you don't give me any tracks to follow this one little error you made at the beginning through, it's tough for me to give you partial credit. So this is why you got to show work, because under a test you might make errors on this stuff. And if I can track it through, we're okay, you know. But if I can't, then it's problems, okay? So make sure your coordinates are good. Or at least mine are good. I think mine are good. Okay, what you gonna do next? I'd find that force is probably what I'd do, yeah, I mean.